that about covers it. And so now it's just to introduce someone that in this room full of Haskell programmers perhaps needs no introduction. I've already seen people bringing up copies of his book to get signed by him. So, you know, and I went into the spiel already in the announcement for it, right? One of the, you know, editors of the Haskell report who has been doing this sort of stuff for years and, you know, constantly has sort of new visions of what functional programming can be like, is going to sort of share with us what he's been working on, and I'm really excited about it. So, thank you very much, Paul, for coming here.
Hello, is my mic working? Nope. We good? All right, we're good. All right, well, thank you, Gershon, for that introduction and for inviting me here. I got to tell you, I'm pretty astounded at the turnout. And I just had dinner, so Dan Winograd Court is a grad student of mine at Yale. That if there are any hard questions, I'll get him to answer them. But we had dinner earlier, and he was saying, you know, when I first got to Yale, which was what, 5 years ago, he said that the ongoing joke was that you could take all the Haskell programmers in the world, put them in a 727, and if it crashed, nobody would care. So here you are, and I know you're not all Haskell programmers, but many of you are, and that's just amazing to me. When we designed Haskell, 25 years ago now, people thought we were nuts. And I guess you could say I got tenure at Yale because of my work on Haskell, but at the same time, I almost didn't get tenure at Yale because of my work on Haskell, because the other faculty members just thought I was in the stratosphere. And perhaps at the time we were, but that's the whole point of research, and it's just been so gratifying to see, really in the last 10 years or even 5 years, how much it's grown. So anyway, thank you all for seeing the light, I guess. It's exciting. Anyway, so I'm going to talk about functional reactive programming, which is something that there's a very simple idea that Connell Elliott had many years ago, which is that why not have a language where instead of variables being something that changes every time you call a function, or an imperative language can change at any time because of side effects or whatever, have them actually be time-varying quantities that reflect a lot of what's in the real world. If you think about many things that go on, it's something, a very simple idea that makes a lot of sense. And the question is, how can you put that into a programming language and make it work in an elegant way? Connell did some early work on doing this sort of thing in C++, and it sort of worked, but it was a bit awkward. And then he and I worked together on doing this in Haskell, and we wrote a paper called Functional Reactive Animation. And that kind of, for me, sparked a whole career of research. I've done other things as well, but you know, the most common thread in my work was, and that was in 1998. So for the last 15 years or so, I've been doing something with respect to functional reactive programming. Yampa was a particular version that we designed at Yale along the way, and since then it's kind of taken off on its own, which is kind of interesting. A lot of papers have been written about functional reactive programming, both theoretical and both practical, but I feel like it still isn't something that's particularly well understood or well known. And so I'm going to give you, I hope, a particular version of it, of what we're doing at Yale at least. And an important related piece of work is one of my grad students, Anthony Courtney, designed a language or a DSL called Fruit in Haskell, which was for programming GUIs. And what you're going to see is a lot of that sort of stuff, but different. And in particular, I'm going to talk about what we've done in Utopia, which is a computer music library that we've developed in Haskell, and what we call the musical user interface, or MUI, rather than GUI. So the whole Utopia thing is motivated not just by I like Haskell and I like functional reactive programming, but there's a context at Yale. We have a new major at Yale called Computing in the Arts, and there are 5 tracks, and there's a music track, and I'm responsible for the music track, and so I teach a 2-term sequence on computer music. So what language am I going to use? Haskell. So that's kind of where this library started. But in fact, the Computing in the Arts major is pretty small, and most of the students in the class are computer science majors that either want to learn something about computer music, but more often just want to learn how to program in Haskell. And I don't require much music background, so I don't require that they have taken music theory classes or everything, so it's all self-contained. So I generally get mostly computer science students. Just so you know, Utopia, the name was derived from Euterpe. It was one of the 9 Greek muses, the goddess of music. And anyway, just an aside. All right, so what's this all about? Well, I mentioned this idea of continuous values, and we call these signals. We used to call them behaviors, but I think signals is a more appropriate term. And for me, it actually was something that I was drawn to quite quickly, because my undergraduate degree was actually in electrical engineering. And a lot of what we do with FRP is really wiring things together in a signal processing-like way, which you're going to see shortly. But you can think of a signal as just something that's time varying. And if you want to think of it as a function, that's fine. So you can think of signal A, polymorphically, as something that, given a time, will tell you what the value is at that time. That's just a conceptual framework. We don't implement it that way. It would be difficult to implement it that way. But, a classic example is, say, a mouse. You have a mouse on your desk, and, if you're programming this in many languages, the mouse rolls, and it sends some interrupt through the operating system, and some callback function wakes up, and then the callback function modifies some global state, so we know what the value or the position of the mouse is, and then the rest of the program sees that implicitly, and so forth. But what is a mouse? I'm not talking about clicks now, just think about the position. It's just a pair of numbers. Why not have in our program something called mouse, which is just a pair of 2 numbers, and it's time varying. And we can use that value to do all sorts of things. So we should have functions that add these time varying things, functions that take the sign of them or integrate them, and so forth. It's a totally simple and natural idea. So it turns out that if you go in that direction, you can do some really cool stuff, and that's what the Fran paper was about that I wrote with Connell 15 years ago. But for reasons that I won't get into, that relate to both efficiency and modularity, we actually use arrows. So how many people know about arrows in Haskell? Wow! That's great. It's especially great because I'm not going to go into a lot of detail about arrows, so it's good that you know what they are. But you can think of, so what we do, the reason we use arrows is, again, for efficiency and modularity, and you can think of then this type, a signal function that maps, a continuous signal of type A into a continuous signal of type B. And again, conceptually at least, it's taking one of these functions and mapping it into another function. So we have input, we have output, but everything's time varying. Okay? So in the arrow framework, and I hope this is especially useful for those who don't know about arrows, the way to think about this is, again, you're wiring together processes in a signal processing diagram. And here's one of those boxes in a signal processing diagram, and I'm making the flow of the signal go from right to left because that's how the syntax turns out, but you could do it the other way. So you have some time-varying x that goes into this box, and you have a time-varying y that comes out the other side. And the way that's written in arrow syntax is like this. These funny-looking arrows, and Haskell's arrow processor handles that with no problem. But in fact, it's actually a piece of a larger syntactic unit, which we call proc. And this is an example of and I think by analogy, this is a good way to think of it. This is a signal function that takes a time-varying x, and it takes that time-varying x, sends it through one signal function, and then adds 1 to the result, sends it to another signal function, and then returns z times 2. Just kind of silly, simple arithmetic. But you can think of this, if you were to write this at the point level, instead of at this signal level, you'd have a lambda expression, right, that applies f1 to x to give y, f2 to y plus 1 to give z. So you can see the correspondence here, and that's why the syntax looks this way, because of its analogy to this, and that's then why we write things right to left in the signal processing diagrams, but otherwise it's just syntax. Okay? So let's do an example. How did I jump? Okay, so it turns out arrows, if you know enough about them, actually expand into a set of what are called arrow combinators, which are part of the arrow type class. And I'm not going to get into any of that in any great detail, but there are a few of them that are just very handy to use. So if you have these signal functions, these boxes, and we want to say compose a couple of them together, this is just 4 simple functions that I'll be using in later examples, which is the reason to show them to you. So first of all, we have a way of lifting a normal function to the signal function level. So our plus 1 will be a signal function that, for this continuous value that's coming in, what it will output is a continuous value that's 1 greater than every point of the input. Const A takes a constant, and just like the const function in Haskell, it's returning a signal function that it's going to ignore the input and just always return b's. So remember, this is the input, so we're going to ignore the input and just return whatever the type of this argument was here. Okay? And then 2 operators to compose signal functions, and the only difference between them is which way you do it. So we have a forward composition and a backwards composition. And it's easy to remember because this looks like it's going forward. So the way to think about this is I have this const 440, and I'm running it into this signal function here, which adds 1 to everything. And so that actually should be the same as const 441. Did I do that right, Tim? So just remember those. They're handy because I'm going to use them. But let's do an example. So this is a pretty low-level example, but this is the kind of thing we do in the computer music world, or at least the audio processing world. So from basic trigonometry, we can derive this equation for sine, and details are not important at all, nor are these details, which is a particular recurrence equation that describes, that basically captures what's going on here, but now in an integer-based sense. So So the point is, this kind of recurrence equation is the kind of thing we like to have in a computer, because then we can implement it nicely. And if you're familiar with Z-transforms, that's a common thing used in signal processing. You can basically think of it as a unit delay. Then this corresponds to this diagram. Okay? Y of n is being defined in terms of y of n minus 1 and n minus 2. So let's look at this for a second. Here's y, and here's y delayed by 1, and this is y delayed by 2, right? And the result is c times the delay by 1 minus the delay by 2. So, and then, you know, it's recursive, right? Because this really is recursive. Even though they're different indices, it's still recursive on y. And so this diagram corresponds precisely to this equation. And then all you need to do then is add the initial conditions, which are these first two equations for y0 and y1. Typically, if you have, you know, an nth order recurrence, this is second order, then you need two initial conditions and so forth. So let's take those same set of equations. Here they are. That's the same thing from the other slide, and that's the same diagram. What does it look like in FRP? Well, it looks like this. So there's, you know, there's some syntactic baggage, but not much. The main thing is that this guy here is this recursive thing. Y is, here it is, c times d1 minus d2, and there's this delay operator that takes an initial value and then delays this result. So y is delayed to give d1, d1 is delayed to give d2, and the result is y. So notice this is a recursive equation. That's why we have this little rec keyword, and it just works. Okay? So that's the general idea. Now, that's kind of boring. It's a sine wave. But to give you a better example, we do, in computer music, we do a lot of what we call physical modeling. So the idea is that instead of creating a sound by sort of ad hoc ways, why don't we take the instrument and try to model it in some physical way to create the sound. And so in the case of a flute, you know, we have an embouchure where it's where you blow into the hole, right? And you have, depending on where your fingers are, you have a certain length of resonance. And so this embouchure delay is literally, I showed you the z minus 1 is a 1 unit delay. Just think of this as many of those, but it's variable, so it depends on the frequency. And there's a flute board delay because on the other end you have sort of two parts, two halves of the flute. And then you have a bunch of other stuff which people figure out kind of empirically. Like the shape of the flute results in a low-pass filter at the end of the bore. And you have this is a nonlinear function that has to do with blowing into the thing. It creates the chaotic signal that makes things happen. And then you have breath, and that's just random numbers, and you sort of put it all together, and it sort of works. So this is it in Euterpia, and again, the stuff at the top isn't that important. It's really just creating an envelope for the signal and so forth. This circuit at the bottom, that recursive thing, is what's shown in red here. Again, using arrows and using this FRP framework, it's pretty much a direct transliteration, if you will, of that diagram. You know, it's recursive again, and you get the result that you want. So it sort of works, but let me, this room is not great for acoustics. It's kind of echoey, but let me just It's a great idea. My TV does that. Let me play that again. So that's with one set of parameters, and then you can hear the breathiness, right? You can hear the tremolo. Now you probably won't be able to hear this in here, but if you don't provide enough pressure, you don't get any sound at all, which is just right. If any of you play the flute, if you don't blow hard enough, you're not going to create, that's where that nonlinear thing comes in. You didn't hear it, did you? Yeah, it's just breath, basically. And here's an increasing, so you can hear with the tremolo, on the peaks of the tremolo, you get a sound, and in the troughs, you don't. And then we can turn it into an instrument. Okay, so this is all great. This works fine. We're working on making it run fast. That's a challenge, and I'm not going to talk about much of that today. Yeah. Yeah. I don't know. I haven't run the parameters so high to know what happens. They'll probably just start clipping or something. I'm not sure. Probably. I'll remember to try that. You mean the...
You know, when it starts to do
the tremolo?
Yeah.
Yeah, so... Yeah, so I forget what these parameters are, but one controls the frequency of the tremolo and the other controls the depth of the tremolo.
It's created analog effect. Or do you just make it fixed?
We make it, well, so the parameter controls it, and then it's fixed within that parameter. But it would be easy to add noise to that, to vary it, to give it a little more realistic thing. We haven't done that.
You could walk over, if we're walking in one of the slides to those slides. This one is blocked by a column. It gets in the middle.
Oh, never would have thought of that. All right, so that means I don't have to trip over my wires too. So, so that works out great, and it's pretty natural. But it's all I'm talking about right now are continuous signals and audio processing. And what we also want to do, though, is handle events. So I talked about the mouse, right? But you also press the button on the mouse, and you make an event happen, or you touch something on the keyboard. So events are useful. You know, we would like to have them. The question is, how do you fit them into this framework? Well, one way to think about events is that it's this continuous value that's nothing, and then occasionally it's something, and then, right? So it actually fits in pretty well. So all we have to do is, say, use the maybe data type. We have a type synonym for it, s-event. And for example, MIDI events would be s-event of MIDI message, meaning there's either a message there or there's not. Usually there's not, and then a message might appear. And MIDI message, if you don't know MIDI, it doesn't matter. It's just turning notes on and off on a MIDI instrument. So the point is, a signal function that works on inputs, takes inputs in, takes events, sorry. A signal function that works on events would have this type. So still the SF, but now we have s-event of, say, T1 and s-event of T2. So when you take this continuous stuff and you combine it with the events, that's what actually creates what we call functional reactive programming, because the reactive part depends on these events. So let's see a little more about that. What I'm going to describe is this MUI that I mentioned earlier. And the arrow for the Euterpia MUI is called UISF. So it's just like SF. Takes an input and an output. And then there's a whole bunch of stuff, and Dan did a lot of this work, actually, of creating various kinds of things that I'm going to show you slide by slide. So the first one is we want to be able to create widgets in a MUI or a GUI, right? But let's think for a second about a slider. A slider is no different from that mouse. It's actually simpler. It's just one dimension rather than two dimensions. But as you move a slider, it's just giving you a time-varying position of where your slider is, right? So if we jump to the bottom here, this just means horizontal, vertical. This is horizontal integral slider, whereas these guys are real numbers. And if you ignore this initialization stuff, which controls the range and where the initial slider position is, a detail that's not terribly important, and just focus on the end here, it takes no input, right, but generates this continuous quantity as its output. Well, there's input from the user, but that's not in the program. Okay? So these types are key. We usually call these signal sources because they don't take any input, they're just generating output. And then there are a bunch of things like text boxes, buttons, and so forth, which you would find in any GUI, radio buttons, and so forth. And they're pretty standard. And again, though, the end type here is what's important. In the case of a checkbox, what we have is that it's a single checkbox, and it's either checked or it's not checked. So it is continuously either true or false. So that's why this is written that way. A radio button, you're choosing between a set of buttons. So which one is on? Well, you just look at this value that's coming out. Okay, so do a really simple example. I have so if you look at, how did I get there? If you look at this first example, sorry, I had this set up earlier and it jumped on me. Look at UI 0. Okay, so this is a complete, but very simple MUI program. What does it do? Well, first of all, it takes no input, no output, because when you run this MUI, well, that's it. That's all there is to it. There's that proc keyword, and then there's that HI slider. So it's just creating an integral slider, and the range is 0 to 100, and the slider position is initially at 1. And no, that's the increment, and the slider is initially at 0. Okay? Takes no input, and it generates this continuous value AP. And the reason I call it AP, so in this musical context, I'm thinking of it as an absolute pitch, which means just an integer from, say, 0 to whatever you want. And it represents chromatically a pitch number. And what I'm doing here, pitch of AP is taking an absolute pitch and turning it into a pitch. What is a pitch? A pitch is a type class in an octave. So it's like C in octave 4 or whatever. And what's it doing with that? It's displaying it. Okay? So there are no events here. There are no interrupts or whatever. There's no state, right? If you just think about, this is all time-varying stuff. AP is time-varying. Therefore, pitch of AP is time-varying. Therefore, what we see in the display is going to be time-varying. So, if we do MU1, can you guys see that? You have this slider. It's labeled absolute pitch. And as I move it, the pitch is displayed in this display box. Okay? Okay, so let's move on. The other thing that we want to do is transform widgets. And there's lots of examples of different things you'd like to do. One example is you'd like to attach a title to a widget. Now that widget may be arbitrarily complex. It may have 30 things in it, and you're attaching a title to that. And then it may be part of something else. So this is all recursive. And so what should title do? It should take a string, which is the title, and some existing signal function, and transform it into the same signal function, except now it has a title attached to it. With display, it does the same thing. Now this is kind of interesting. So we have this UISF that generates Bs. And I would just like to see what's coming out. So for any showable B, I'm converting that guy into another UISF, which will have this display attached to it that says what its output value is. Kind of think of it as debugging, but it's actually something you want to do pretty often. Pad just puts space around, so this is for the layout part. Put space around a UISF. These are relative things that say, let's orient these guys top down, bottom up, left, right, left. The example I just showed you earlier, that you might infer from that the default is top down because they appeared that way. But you can change it. And you can also, again, details aren't important, but you can say precisely how big you want it and those sorts of things as well. So I'm going to run a quick example of this. Which is MUI 2. So what does MUI 2 do? It takes this slider, and it has a title on it, which we've already talked about. And it takes the pitch, but it's attaching pitch to the display, so, or title to the display. So it's not too much different. Oh, right, I forgot to point out. So probably the main thing is there's this left-right guy here, which is going to take that thing that was top-down and turn it into left-right. So you get the same effect. It's just that the layout is different. All right, so this is tedious, sorry. It's kind of slow switching. Okay, so this is all great, but what about the reactive part? So the thing is, we want some way to create events, and we want some way to react to events. Okay, and the reason I call these mediators is because a lot of times what's going on is you're mediating between the continuous and the discrete. So an example of that, which will be in the example that I'll show shortly, and it's the only thing that I want you to look at here, is that very top one. It's called unique. And all it's doing is, if I have a if the input A is something that can be tested for equality, okay, then what this is going to do is look at that input, and if the input ever changes, even a little bit, then it's going to output an event, okay, of that value. So whenever the input changes, then we get one of these events. So how does that work? Okay. So this is UE or MUI 3, okay? And what's it doing? Well, again, it's doing the same stuff, but whenever the absolute pitch changes, now remember this is an integral slider, and integers are comparable, and so as I slide it, and as it bumps from, say, 10 to 11, then this guy is going to generate an event. So this event, then the question is, what do we do with that? Well, so I'm introducing something new here, which is that I have some MIDI output device that knows about pitches, and details aren't important, but I have to basically translate this pitch value into an actual MIDI event. And this is what that MIDI event is. And events are in the functor class, so I can use fmap to make these things work right. And what does that mean? That means that as I change the slider, every time I get a new value, I'm actually going to hear what that new value is. Of course, this is a chromatic scale, so it's not very interesting. Nevertheless, oh, sorry. Pardon? Yep, you could. So there's a whole bunch of music stuff that I'm not going to tell you about that's part of Uterpia that does a lot of that kind of stuff, okay? But I'm trying to focus on the FRP stuff here. So here we go. Same thing, it looks the same, but now, as I change this, so there you go. Okay, so oh, I'm supposed to do MUI 4 too. So MUI 4 I'm not going to do MUI 4. It's not adding much. Let's go back to the slides. All right, so what else do we want to do in this MUI framework? Well, one thing we like to do is deal with time, in the sense that we like to have timers and a notion of what time it is. This can be very useful in a musical context. This part of the design is actually changed, right, Dan? But I'm running an old version of the code. Anyway, the main thing here is that you can have a timer. So you can say, give me a sequence of events, okay, that are spaced by a certain amount of time, okay? But there's something really important going on here. This is saying what that time is. Sorry, this is saying what that interval is between the events. But notice that it is a time-varying input to UISF. So this timer is actually a time-varying timer, right? So what does that mean? So suppose I were to, suppose I wanted to create a MUI that had a slider that controlled the pitch and the rate at which I want to play that note. So it's a variation, a bit, of what I showed earlier. So look at MUI 6, or MUI 5 here. Nope. MUI 6. Okay. We have this tick, which is this timer, and it takes this frequency component, but what is F? F is just the output of this slider. Right? So you just feed the slider. So again, you're just like wiring circuits together. You feed the slider into this timer, this variable timer, and you take that tick and you use it to govern when you play the notes rather than the unique thing. Okay? So if I do MUI 6, Oh, sorry, was it 6? Yeah. You can hear that very low noise. Let's make it even faster or higher. There you go. So, you know, I think the code's pretty simple and it reflects exactly what we want to do. And I think that's a key of any kind of programming. So, does this have any practical use? So there was a well-known computer music guy his name's Gary Lee Nelson. And way back in 1995, he created this composition and got quite a bit of attention for it. I hadn't made it full screen. So, what's behind the scenes there? Well, behind the scenes, the reason he called this piece Bifurcate Me Baby is because he used a simple equation from chaos theory, which I'm not an expert in at all, but that's the equation, and it basically models population growth, like on an island where you have the foxes eating the rabbits and whatever. I know people do this kind of stuff, I just don't know the details. But anyway, that's a simple recurrence equation, right? And if we were to code that in Haskell, it would look very simple. We really have 2 parameters here, and we're just creating this. So grow is just creating the next value from the previous value. Okay, so we have a rate, and we have which is r, and the value x. So we can wrap that up in a MUI, and again, take a look at it very quickly. Sorry, that's some other example. So here is the growth function, grow rx, that I just showed you. And then there's something that converts it, one of these values, into a note, which can be done in lots of different ways. Details don't matter at all. And then this is the entire MUI. Okay, there's a frequency slider, there's a growth rate slider, there's a timer. So that frequency controls this timer, and it kind of does the obvious thing. So that's, you know, the whole piece of code. And you can view this as a way to experiment with this kind of composition that Gary Lee Nelson was doing. So if I come here and say bifurcate. So what's interesting about this function, you see it's oscillating between 2 values. As I increase this, it will settle in sometimes to 2 values, sometimes to more. So that's 2. I think that's 4. So it's bifurcating, right? But eventually it goes into chaos. And that's basically what Gary Lee Nelson was doing to make this composition. So, enough of that. All right. So, let's get back on track. And let's get a little more nerdy here. Forget the music. So, the idea of this FRP seems to work out pretty well, I think, but it has some problems. And one of the problems that bothered us along the way is that the entire program is a signal function. So if you're doing any kind of input or output, you have to kind of run everything here for input, you know, and then so you're multiplexing and demultiplexing, if you will, these values, and then on the outside you're doing the opposite. And that certainly is not something that is very modular, or you could argue that it's not modular. Even though it has advantages over what we initially did with Fran. In Fran, external devices were just these global things that were defined and they just existed. So it was, in that sense, it was very unmodular. This we actually thought was an improvement because now we could say which devices were going where and so forth, but it's still, the problem is you have these bottlenecks, right, on the front end and the back end. And that's kind of unfortunate. So what can we do about that? Well, why not treat these external devices, as I was arguing earlier with the mouse, as actual signal functions, okay? And sort of suck them into the program, or the other way to think about it is you're expanding the program out to now consume the world, if you will. So you're, if you do that, you end up with something like this. So now I have, so this was my original program, but now it's very specifically, you know, SF6 only deals with the printer and console I/O, right? And each of these guys, and even ones like, say, an electric piano or a synthesizer, it may take both input and output. It's just a signal function. So all of these boxes, this is a signal function, but so is this, right? This is a signal function, so is that. Why not do that? And that's a simple but kind of key insight that that we pursued. Problem, though, is that in a program you can duplicate stuff, right? You can create as many occurrences of something as you want. But in the real world, I've only got one digital piano, or only have one synthesizer card, right? So we call this the problem of resource duplication. And a classic example is, I already showed you this MIDI out thing, and you say, oh, it looks great. But it's not so great because what if I do this? What does that mean? I only have one MIDI out card. Does it merge those two note lists, or ignore one, or non-deterministically, you know, what's going on? And with MIDI in, you could kind of give a better argument here. You could just say, well, you get exactly the same thing in both cases. But still, it's a little bit uncomfortable. Okay? So, that's a problem. How do we solve that problem? Resource types. So this was the second term in the title of my talk. And the idea of resource type is fairly simple. Implementing it is a challenge. But the idea is that something like a MIDI synthesizer, say, may take MIDI messages as input and return nothing as output. I should have probably just written this as MIDI out. But in any case, the point is we're adding an extra argument here to the type. It's a phantom type, okay? And that phantom type we call resource type, and is basically a set of resources, but implemented at the type level. So this S just means singleton set. So the MIDI synth consumes, if you will, one resource, namely the MIDI synth resource. And random SF, I should have changed that name as well, but it's if you're doing random numbers, you have a similar situation. If you have two random number generations, are they independent or are they the same? So you have an issue there. These guys are singleton sets, and the point is that those previous examples I showed you now won't type check if you implement these types in the correct way. So these examples won't type check. Why won't they type check? Because of this. So here's that expanded type now. It's got this extra argument R, right? That's the set of resources. And if I have one signal function that has this type, another signal function that has this type, I don't know why I wrote V there. That should probably be C. So the idea is I want to compose these two now using this operator. So if I compose them, then I go from A to V, but I meant C. But the point is that won't type check unless R1 and R2 are disjoint. And that test for disjointedness has to be done at the type level. Okay? And I'm not going to get into details of how that works, but we use type families and, higher order kinds and that sort of thing to make it work. It turns out that you can at least implement, in this way I just described, a restricted form of this idea. But to do it really cleanly, we need some extra extensions to Haskell which don't exist. And that's the story of Haskell, isn't it? People need something and they figure out how to do it and they tell Simon Peyton-Jones to put it in and he does. So
Now he just gives them permit access.
that's right. So we'll see. That's Dan's job. Okay, so I'm on to my last topic. Am I doing all right on time? Okay, so let's talk more generally. What does it mean to do side effects in FRP? Okay, so in a way, this I/O stuff is sort of side effecty, but we've done it in a pretty clean way. If we're not using FRP and not using arrows, well, of course, you just say, use monads, right? And I/O, the I/O monad, right, is what we use in Haskell to do effects in the real world. If we're doing effects within a program, we typically use the ST monad, which does this little type trick to make sure that everything is safe. And it more or less works. But I think it's important to understand that those two are really pretty different. Okay? I/O is for real-world objects, and the point is that they can't be created on the fly, typically. You don't suddenly create a new printer. It just doesn't appear. Whereas if you have a mutable data structure, you may create many instances of that in a program and in some arbitrary way, and they can be allocated dynamically. In both cases, the monad provides the sequencing we need in order to do the side effects. Okay? But the question is, what does that translate to in FRP? Well, remember that events in FRP is the sequence of things, right? Well, why not use that? So what we do is essentially use the ordering of events to kind of be like a monad. Like one event comes and then the next one comes and things are being sequenced. And if you think about the MIDI in and MIDI out example, that's what's going on, right? And how you write your program to merge the events that go into MIDI in and MIDI out affects what results. Just like in a monad, depending on how you order things, you get different results. Okay, so that's actually the easy part of the story. What about mutable data types? This is why I was saying earlier that the distinction between real-world stuff and internal mutable stuff is somehow fundamentally different. Well, one thing you can do in FRPs pretty straightforwardly is you can define something that you send it a request to update some array, and you get a new array that is the modified thing. And you don't even have to create an entire array here. These requests and responses could be, set the variable and now tell me what the next value or the value of some position is. And that can all be done in place in a totally mutable way. And in fact, to do that, you don't even need resources type. You don't even need resource types. But let's explore this idea a little further. Let's consider, instead of an array, let's consider a single variable. Okay? So we're going to call it init. And the reason we call it init is just because it relates to our work on causal commutative arrows, which I'm not going to get into. But the idea is I send a value in, and it replaces what was there. Okay? And on every tick, I get something out. So it basically amounts to a delay. Remember the z minus thing? It's exactly the same thing. Z minus 1, init, delay, they're all words for basically the same idea. Okay? So let's explore this. So this is about the simplest case of a mutable data structure that you can come up with, right? Just think of it as an assignable variable in a way. Okay? Well, let's look at init a little more closely. What if we were to split the reading and writing? Dan, I don't know how you did that. That's so cool. I should have mentioned that the last few slides I stole from Dan's talk. What if we split them up? What does that mean to split them up? I want to try to separate the writing from the reading. Okay? So, let's do that. And that yellow or green or whatever color that is, wiggly line in the middle is magic. Right? So I'm going to write into this black hole, because the black hole sucks up everything, right? And I'm going to pull out of the white hole. And this stuff in between just magically happens. Okay? So basically a wormhole is a pair of a black hole and a white hole. Okay? Well, that's weird. So I call it splitting an atom. That's new, Dan, right? I changed that on his slide. That wasn't his title. So the point is, we can think of these as non-local, one-way communication channels. That's a serious effect. Okay? That is an effect in a language. So we want to do this. We want to do this dotted line. We want SF2 to magically communicate with SF1. Okay? And normally, we'd have to do something like this. Suppose I wanted to do that. Say, oh, geez, I got to refactor my whole program. I have to take whatever it is I want here and send it to the output, and then sneak that into this input and run it in over there. Right? I've changed all my type signatures and everything. Right? Non-modular. This is what imperative programmers use as an argument against functional programming sometimes, right? So we want to do better than that. Use wormhole. So I haven't changed any output here or any input here. All I'm doing is throwing in this little... So I need to create this pair, this wormhole, a black hole and a white hole. And then over here, I write to the black hole. And over here, I read from the white hole. But these guys are intrinsically related. There's got to be some more physics analogies to this, right? What are those particles that interact from a distance? What are they? Cool. So maybe we can...
Spooky action at a distance.
Spooky action. So this is spooky action going on here. Anyway, so that's the idea, except we still have a problem, which is that we can't duplicate these black holes and the white holes. So we need resources types to make sure that we don't do that. So that's how all this connects, right? So the resource types prevent me from writing to this black hole here, and then it's just a value, right? I could write to it down here or something, and then I have the problem, what does that mean, right? I just say I can only have one of those, and I can only have one of those, and they come in pairs. So we use resource types to make it all safe. And here's an example. So the SF1 here is now just, well, let's look at SF2. It's taking some local data that it wants to communicate magically elsewhere and sends it into the black hole. And the corresponding white hole is up here in SF1, and it's just being read from, and there it is. Yeah.
How do you tell which black holes and white holes in the code?
Right. So, how do you tell which white holes go with which black holes in the code? So there is a function for creating a wormhole. It's a, make wormhole, and it returns a pair. And that's the pair that you use. And then the pair is resource typed, so that when you pull the two components out, you can only use each of them once. So that's how it works. But there's actually more to getting all the semantics to work, and that's part of Dan's dissertation. And I'm sure he'd be happy to tell you in great detail. So that's it, actually. I was going to play you something that one of my other graduate students, Danya Quick, is a pretty talented composer and has done a lot of cool stuff and won some awards for stuff. This is just one thing. I'm going to play it. And maybe I won't play it too loud and I can answer questions while it's being played, because it's a pretty mellow piece. She actually won an award for this. There's some online competition. Like every couple of months, they have a theme, and you're supposed to submit something consistent with the theme. And for this entry, it was bells. So all these bell sounds are not sampled, they're not MIDI, they're all created in Utopia using the signal processing stuff. And so there's a lot of interesting bass going on here that you can't hear well through these speakers. She created all the sounds and then composed the piece by hand. But she's done a lot of automated composition as well. Maybe I'll stop it there. Oh, it's starting over. There we go.
Which database do you use to store all the data? Which database platform do you use to store the data?
Say it again.
Which data storage? Which data platform you use to store the data?
What platform?
Yeah, like, for example, the backend for the music.
Oh, okay. So we use port MIDI and port audio for the sound part. And we use GLFW for the graphics. And it runs well on Windows and Linux, and not so great on Macs right now because we don't have anybody in our group that is using Macs, and Mac platforms just change constantly. It's been a real challenge for us. Anyway, go ahead.
I noticed earlier in your, when you did the matrix of chords,
Yeah.
they're all in second position. Is that so that the input person can, or the input mechanism can supply the root?
Which chords?
When you went back to your minor ninths, your minor, remember you had the little array of,
Oh, you were looking at parts of the code that I didn't actually do. Yeah.
well, it's in your book too.
It's in my book.
Yeah.
You've been reading my book.
Yeah. I was just curious. I was taken with the idea that as I was looking at it, it was that all the chords were root, excluded the root, in a sense it dumped the root to the top of the chord. So I was thinking, was that so that the input mechanism could supply the root and then the chord would be stacked on top?
I can't remember.
I mean, it seems it's trivial, but
You're talking about this stuff here.
yeah.
Oh, these are intervals.
Yeah, I know. But the way you've written them out, they're sans root.
Oh, I see. So the root is 0.
Right.
So the first interval is 4.
Right, but am I as the operator? Am I supplying?
Oh no, this
Then
is.
then they're written in second position.
What? These are intervals.
Yeah, I know, but they're written out in second position. You're
No, but if I
starting
have-
on. Yes, I know, but you have to start with the root, and the root's not included.
No, the root is always 0.
Yes, I know the root is 0, but you don't illustrate the root as 0.
I think we can move on.
No, I'm sorry. I found.
It's a. You could do it another way.
Well,
This, I think, was the
modes that way.
modes.
Yeah, using modes as decided by purely invalid.
Yeah. So, right. There's a little bit in my book about modes, but yeah, there's tons of ways to. Okay. Got it. I found generally that intervallic relationships, chords, and harmony are much nicer. Yeah. Yeah. Exactly. So. I don't know. That was kind of the motivation here, I guess.
The way they were notated, I was like wondering if the input operators applying roots, and then the chord built up on top of whatever the bottom value.
Oh, I'm sorry. Yeah, I see. Yes, that is what's going on here. So I would do this. I would run this MUI for you, but it takes as input the keyboard, and I don't have a keyboard.
That's how it works.
Yeah. So if you press a C, then it'll use these intervals to construct a C major 7 or D major 7. Sorry, I wasn't understanding, but I think we're on the same page.
So I appreciate that all this is done in the context of music, but it seems that there's a lot of stuff in your framework that's not actually specific to music, and I was wondering how easy it would be to build like a circuit simulator using this framework.
Yeah, good question. So, well, a couple things. First of all, Dan has just recently extracted all the MUI stuff out into a GUI. Instead of calling it MUI, all the stuff that's non-musical. So I didn't show you, but we have widgets for keyboards and guitar frets and things like that. So those are music-specific widgets. But the basic framework is completely independent. The sliders are useful in lots of contexts. And we're pulling all of that out, and we're going to release that independently of the Euterpia stuff. And the sound processing stuff is a different arrow. And it's different not just by name, it's fundamentally different. When you're doing audio processing, the notion of events becomes not nearly as important, if important at all. And furthermore, the time steps, you know. It's you're doing, in the case of audio, typically 44.1 kilohertz. And that makes implementing it a lot easier and we can make it a lot faster. And so, so if you just look at that stuff, again, it has not a whole lot to do with music. It's just really signal processing. And it starts to look more like what we did with Yampa many years ago, which was pretty general purpose. So it would probably be good to pull that stuff out as well, the generic part of that. So. In the back, you had your hand up first, yep.
Just looking at the field of the tiny lot issues, you have to use building up grants. In other words, we construct things that feedback themselves.
Yeah, several examples I showed you did that. And in the arrow syntax, there is a ret keyword that says specifically that this section of the arrow code is mutually recursive. That's very important in signal processing. The sine example and the flute example both were recursive. And you can get bit if you feed X directly back to X. There needs to be a delay somewhere in there. And there's been some work by Henrik Nielsen to actually create a type system that guarantees that there's at least 1 unit delay in every recursive loop. But I'm not sure it's worth it because it's pretty easy to tell. I mean, it's like in Haskell, you can write an infinite loop, right? Or you could use a language that is based on, pure lambda calculus with typed lambda calculus, where you don't have a fixed operator, but then it's just really hard to program a lot of things. So I prefer having the freedom to write the recursions the way they're most natural and risk the fact that I might end up in a black hole. That's a contentious statement, but that's where I'm coming from. Yeah.
Do you consider the
Mathematica? Oh, Max MSP. Yeah. Well, I think Max is a cool visual programming language that makes it really easy for people to do things pretty quickly, but has some serious design flaws from a language point of view. I don't think that graphical languages scale at all. It's really hard to make changes to, I've seen some students at Yale that have created these unbelievably complex webs in Max, and it's terrible. and Max doesn't have high order functions, or we can say all the good things we like about Haskell, but I don't know how anyone can program in any language without high order functions. I just don't get it. And oh, I see what you're saying. Oh, I think so. I don't know what FRP means, even though I promote it. We usually think of it as being part of functional programming, and I don't think of Max as a functional programming language. It has some weird things, right? The ordering of the inputs and what triggers what. I don't know. It's just very operational to me. I wouldn't say it's imperative, though. So you could make an argument. I won't. Yeah, I won't deny that. Yeah.
Numerical issues. So, do you run into numerical issues? So, where you could set up a circuit which is mathematically correct, but integrated with doubles, it doesn't actually work.
Yeah, integration is usually not a problem, but if you try to differentiate, you can run on all kinds of instabilities, and that's always a problem when you're dealing with numeric. I haven't run into those kinds of problems in what we've done, but it's certainly possible to run into those.
Perhaps a circuit would naturally associate with hard dealt with some different types of like it's hard to model
Yeah, well, I mean, but that's right. In the case of audio processing and computer music, those problems are pretty well known, and people have different ways of dealing with them. So let me give you two examples. One is clipping. That's actually a pretty hard problem because you have to look at your entire, not just your final output, but everything in between to see if anything clipped. And it's easy to do. And the other example I was going to give is well, I don't know if that's a good example. Well, clipping is a good example. Arithmetic in computers it's not very mathematical, right? If you're working with doubles or floats, you don't have distributivity or anything like that, and you can get some weird problems. And you just have to be careful. In Utopia, I try to, when we deal with things like duration and things like that, we use rational numbers everywhere. And Haskell has infinite precision rational numbers. It's arbitrary precision rational numbers. And I find that the overhead of that isn't so great. I prefer to use rational numbers to floating point numbers when I can. But when you're doing every bit of the output for a wave file, you really need to use doubles or floats, and then you can run into these problems.
I was wondering if there's any relationship between your resource types and uniqueness types of clean or regions for kind of other resource management.
Well, there's a sort of a general connection in that they are all trying to solve this, kind of resource control or linearity kind of condition. But it's really pretty different, especially from, uniqueness types in clean. You're still threading everything through a clean program, if you know how that works. You have a world and you do something with the world and you get a new world, and you thread it through, so it has more of a monadic feel. And the type system there is more to simulate what monads do than anything else. Whereas what we're doing, I feel, is, I think in many ways, much simpler. You're really just saying, I only want to use this resource once. Which then raises a question, what about linear types, which are more address that kind of issue. But even there, I don't know. I think it's different. What do you think, Dan?
So uniqueness types can be. The point about the monadic bit is pretty important.
The point Paul said about how uniqueness types are more like monadic sequencing is pretty much the big difference between that and something like resource types, like what we're doing. The other The other difference that you can notice is that in an FRP program, we kind of assume that everything's infinite. And so once one signal function is using a particular resource, it can't give it up. It can't say, I'm done with it, because it's kind of running forever. So you can have some idea of switching, and then you end up modeling something that's very much like uniqueness types and very much monadic in feel. But in kind of the pure arrowized FRP that we're looking at, resource types feel very different because of that way that they can't be given up. Once something has a resource, it will always keep using it.
So further questions?
Anyone else? All right.
Okay, well, thanks again, Paul, for a wonderful talk. Andres didn't make it down, did he? So, as is usual at the end of our meetups, we have hiring announcements. Hi, S&P Capital IQ. We're still looking to interview people. Not in Haskell per se, but we do some stuff that's very interesting and involves that in-house Haskell-like language. And we have taken inspiration from whiteholes and black holes, and I can tell you about that. So that's very cool. Andres Vormi, I was hoping was going to come down because he wanted to announce. He's not here. I'll get him to send out his email to the list. I know he wants to talk to people who are interested in perhaps working in the Connecticut area and are interested in Haskell and ideally know something about switching and computer networks, I think. But he would have to explain it in greater detail. But that is an interesting thing coming up. Does anyone else have any job or hiring or other general interest announcements? Right. And then we'll do the pub announcement, the most important.
Hi, folks. My name is Ray Lacaz, and I'm one of the organizers for Lisp NYC, and I just wanted to reiterate the point that Gershon made earlier. What we're trying to do this year is we're actually trying to organize a functional language holiday party, and we've invited all the, we've networked with all the organizers of all the various functional language groups, including Haskell, Erlang, OCaml, Clojure, and we really do need to know that Lisp NYC won't be footing the bill on this. So we really strongly encourage you. This is, the Haskell meetup and the Lisp NYC meetups are the two largest FL meetups in New York right now. So we're really kind of relying on this community to step forward and just pitch in whatever capacity you can. But we'd really like to make this happen. I think it's a really awesome thing to have all these FL communities have a communal holiday party. So thanks.
All right, guys. So after this, as usual, we're going to a bar to hang out. You can meet the speaker. You can meet a bunch of other interesting people. The place we're going is called Jake's Saloon. It's at 206 West 23rd Street, which is the southwest corner of 23rd and 7th. I'm sure you can find a group to follow as well. Thanks.
Hey, one more hiring announcement. Over at patch.com, a couple blocks up, we're doing a bunch of Scala work with heavy Haskell leanings. So come talk to me, and thanks.